In this particular lesson, what we're going to talk about is the electromagnetic spectrum, but in a more specific and detailed manner. Specifically, we're going to talk about what's called the atomic spectra. And essentially, the atomic spectra is a series of emission and absorption spectra which contains specific wavelengths unique to each element. So, how do we get to that? So, one thing that I wanted to point out to you guys, and I think that we have all known about how prisms work when it comes to spreading out white light into the respective visible wavelengths of light that we consider a part of the rainbow. And I'm kind of borrowing from Pink Floyd here, where they have a prism in the center and some white light traveling to that prism, and the prism will diffract and separate all of the wavelengths of light into multiple wavelengths that you can see here. So this would be the Roy G. Biv wavelengths of light that you see in the visible spectrum. So when we tend to look at an atomic spectra, whether it be an emission spectra or an absorption spectra, we tend to look at it like what we see down below at the bottom of the screen, and this called a continuous spectrum. And the continuous spectrum it shows all of the rainbows of the visible wavelengths of light along with their respective wavelength measured in nanometers at the bottom. So this is very nice to be able to separate wavelengths of light in a spectrum so that you can see all of the various visible wavelengths. But something very interesting happened in the early 1800s. And what happened were these two scientists, William Hyde Wollaston and Joseph von Fraunhofer, in 1802 and 1814, actually started looking at sunlight or solar light and using a particular prism and spreading apart the various visible wavelengths of light in that visible spectrum. And it turns out that William Hyde Wollaston noticed that there were actually sections within the spectrum that did not actually show any colored wavelength. In fact, they were like black lines. And this was when he was taking sunlight. And so Joseph von Fraunhofer he was really good at making really good quality prisms and was able to make a better prism than Wollaston was able to do. And also did this experiment, but then started to go through and calculate what was the actual wavelength of all of these missing black lines. And he was able to do this for over, say, like 500 different wavelengths. And what he didn't understand, though, at the time was why were there specific wavelengths missing? And so this is where we move to talking about two new scientists, Robert Bunsen, who is coined with making the Bunsen burner, is why we call it the Bunsen burner, and Gustav Kirchoff. And what they did was they actually took a Bunsen burner like Robert Bunsen had made and started burning elements in the burner, and then would pass that through a prism and look at what colors it would emit. Well, the video or picture that I have shown here is not the actual burning of elements in a Bunsen burner, but instead you can do this exact same experiment with hollow tubes that are filled with a particular gas form of an element. In this particular case, we're using hydrogen. And then you can narrow down the light being emitted from hydrogen when it's electrically charged through a slit and passing that slit through the prism. And it turns out for hydrogen, you don't get an enormous amount of wavelengths of color. In fact, most of the visible spectrum is black, and you only really see 4 different colors come through the prism itself. And it turns out if you actually figure out what their wavelengths are, you have wavelengths of around 410 nanometers, 434 nanometers, 486 nanometers, which are your violet, blue, and light green colors. And then one over here in the 656 range, which was a red color, which was really interesting. And so it turned out that whenever you actually pass electricity or have an element give off wavelengths of light through whatever method you give them energy to do so, they can provide their own wavelengths of light when those electrons release that energy. And so there are 2 forms of an atomic spectrum that we will start to use now in chemistry. The first one is what we call an emissions spectrum, and that's the one that you just saw in the previous kind of slide up there, where you only see the wavelengths of light that are emitted by that element. So they're giving off that wavelength of light. And the other kind of spectrum is called an absorption spectrum. But the absorption spectrum should be the exact opposite of an emission spectrum. And this is where these are the wavelengths of light that are absorbed by that element and not emitted. And so more often than not, we will look at and use the emission spectrum when we're looking at particular substances and using an atomic spectrum to identify them. And it's really interesting because it turns out all elements and compounds have a unique line spectrum or emission spectra. And so use this one as a reference where all of the wavelengths are light and are in the continuum top reference. And then if you look below that, this is hydrogen, helium, argon, nitrogen, neon, mercury, and CO or carbon monoxide. And so each one of them absorbs and emits different wavelengths, which we can now use these to identify a substance by just electrically charging them and letting them emit light and being able to diffract that and find their emission spectrum pattern. Now, this is all nice, but how does this play into the role of what the atom looks like? Well, it turns out that there were 2 scientists that did some really good work with the line spectra. The first one in 1885 was Johann Balmer. And what he did, this guy is a Swiss mathematician that looked at the line spectra and thought he could mathematically use an expression to explain how the different quantized values that Max Planck had several years before described, and figure out what wavelength a particular line would be on a spectra. The equation that he used was this equation here, which is the wavelength equals h times m squared divided by m squared minus n squared. Now don't be confused by this h. It is not Planck's constant. Instead, at the time, he called this Balmer's constant. We do not use an h for that or even really this equation anymore. So this is here just for you to be able to view. Now, the constant for Balmer's constant is 3.6456 times 10 to the minus 7 meters. And the M and N refer to different quantized levels that Max Planck had suggested, and Albert Einstein had even suggested it used with his photoelectric effect paradox explanation. The interesting thing about this is that N is always 2, and M is 3, 4, or 5, or higher. And guys, I just realized that I might have messed this equation up. It should be N and M here. Sorry, I apologize about that. So N should be the smaller number and M is the larger number. And essentially what you could do is, as an electron, if you will, moves from a value or a level of some N number to the N number of 2, you could figure out what wavelength of light it would emit. Now, a few years later in 1888, Johannes Rydberg, who was a Swedish physicist, also was looking at the line spectra and trying to explain exactly how that line spectra correlated to wavelengths of light and how that could then be translated to the atom. And what he did is he came up with an equation that looks somewhat similar to Balmer's equation, except for he did not specify that N had to be 2. So this first value here did not have to be 2. Instead, he used the term low and high. So if you had one level that you knew that you wanted to move an electron from, say, 3, and it was coming from a level of, say, 7, then the number that you would put for N low would be the 3, and the number that you would put for N high would be 7, just whichever one's the highest you put as the N high. And in this particular case, the R in the equation, R sub H, is actually a constant that we now do call Rydberg's constant, and that value is 1.097373 times 10 to the 7th per meters. Now, this is a constant that you do need to put in your toolbox of memorization, so keep that constant. I gave a very long constant. I think this is 7 sig figs, but if you want to use a 3 sig fig constant of 1.09 times 10 to the 7th meters or per meters, that is fine also. But the really interesting thing about this is that this equation we can actually now use in order to determine if an electron gets excited through some electrical current and an electron's moving from one level to another. We can figure out what line or what wavelength in the emission spectrum it will project off. Now, none of this work at the time, so Johannes Rydberg and Johann Balmer did not actually develop any structure of the atom. But there was a scientist years later that was able to use Johannes Rydberg and Johann Balmer's work, along with Max Planck's work and Albert Einstein's work, and even another scientist called Ernest Rutherford. And he developed this thing called the Bohr, what we now call the Bohr model. And this was Niels Bohr. When we move into our next video, I'm going to talk about the Bohr model in more specific detail and how the line spectra and the Bohr model and Max Planck with the quantized model all fit together. But before we go to do that, I want us to try one particular problem of how to use Rydberg's equation to calculate a wavelength of emission. So let's try this example. It says use the Rydberg equation to calculate the wavelength in nanometers of the light emitted when the electron in a hydrogen atom undergoes a transition from n equals 3 to n equals 2. So remind ourselves of what the Rydberg equation looks like. Is 1 over wavelength equals r sub h times 1 over n squared low minus 1 over n squared high. Okay, so let's figure out what all of our variables are. Obviously, we're solving for lambda, so we don't have that value, but RH we know is a constant, and our constant for that is our 1.097373 times 10 to the 7th per meters. Our N low is going to be the lowest out of the two N values, so this will be 2. Our N high will be the highest, so that will be 3. So now we just plug everything in and solve for wavelength. So we have 1.097373 times 10 to the 7th per meters times 1 over 2 squared minus 1 over 3 squared. And that will equal 1 over wavelength. So if we plug in Rydberg's constant and do all of the math in the parentheses, we end up with a value that looks something like the following. 1524129.167, and then the units will still be per meters, and that's what the 1 over wavelength equals. But keep in mind that's not the answer, that's the reciprocal of the answer. So we're going to solve for wavelength by putting 1 over 1524129.167 per meters, which when you have a per meters on the denominator, that really is meters. And so we just do 1 divided by that value, and this should give us the value in meters. So this is 6.5611237 times 10 to the minus 7 meters. So if we want to put this in nanometers, essentially we need to convert our value in meters to nanometers. And so to do this, we essentially need to multiply this number times 1 times 10 to the 9th, because for every meter there is 1 times 10 to the 9th nanometers. Our meters will cancel out and this will put us in nanometers. And so if we're going to go with significant figures, we'll consider 2 and 3 exact values, but our value of Rydberg's equation is a total of 7 significant figures. So let's put our answer in 7 sig figs. So it's 1, 2, 3, 4, 5, 6, 7. So that means our value, when you put this in your calculator, ends up being 656.1123 nanometers. All right. And so if you turns out, if you go back and look, so 656, so keep that number in mind, at the hydrogen emission spectrum, right here, oops, for the red line, that value is right in the value of 656. And so 656 nanometers is the red line in the emission spectrum of hydrogen. And I just noticed that there is a typo here. This should be 700 nanometers. Right there. Okay. If you happen to have any questions about how Rydberg's equation works, or want some more practice problems, email me or post a comment on YouTube, and I can send you some more practice problems to do. I will see you in the next video where we talk about the Bohr model.